Okay, so this is Unit 5, Ratios, Proportions, Rates, and Linear Relationships. Some very important topics for middle school math students, and also in life, whether we're dealing with bulk buying and the price of items, whether we're dealing with rates including speed or other rates of change, including growth. So some very important concepts that we're going to discuss here. So please attempt the questions yourself if you have the worksheet, and then watch the video. You can pause it at any time, and if you don't understand something, sometimes watching through a question 2 or 3 times could really help as well. Okay, let's get started. Okay, so question number 1 here, we have a list of items, a list of objects, and underneath we see that the objects are things like mice. There's some mice there, and also there are some timers there as well. And so here are our timers, the little hourglasses. We've got 1, 2, 3, 4, 5, 6, 7. So this is even before I've gone into the question. It basically says in the list of items below, what is the ratio of, and then we're looking for the ratio of mice to timers, timers to mice, and timers to all. So this is just really a quick start. We've got 1, 2, 3, 4, 5, 6, 7 timers. So I would put timers equals 7. And then for the mice, we've got 1, 2, 3, 4, 5. So I know that the mice equal 5. So a ratio, something that's very important to remember, is that a ratio is a comparison of 2 amounts, and we can write ratios in a few ways. So mice to timers is 5 to 7. So often we write ratios in this way, 5 to 7. So we've used a colon in the middle. Another way that we could write a ratio is 5 to 7. That's one way to do it as well. And finally, we could write this as a fraction. Ratios of fractions, 5/7. That's another way for us to write it. So B, timers to mice. So this time it's the other way around. It's 7 colon 5, 7 to 5. And for C, it's timers to all items. So in this case, timers, we've got 7. And all items, well, all items are just adding these. So 5 plus 7 gives you 12. So 7 to 12. And that's all that's required for question number 1. Okay, question number 2 is a little more wordy. So it's really important that we try and highlight the parts of this question that are very important. So you're stocking up on toilet paper, and you see that you can buy 16 rolls for $10. So that's pretty important, so I'm going to highlight that. How much would it cost to purchase 40 rolls at the same rate? So that pretty much means that the price per roll is going to stay the same. Now, it's also important that we keep in mind that what the question is saying. So the question is saying, how much would it cost to purchase 40 rolls at the same rate? But then we're also told to write a proportion to solve and find our answer. So this really is a great starting place for us, because we've highlighted everything that's really needed in this question. So we're told that 16 rolls are $10. So I'm going to put a little R here for my rolls, and I'm going to put a $sign for the price. Now we were told that 16 rolls, so I'm putting 16 where the R is, gives us a price of $10. So I'm going to write this as a ratio. We're comparing 2 amounts, 16 to 10. We could have done it the other way around and just made sure that we kept everything dollars on top and kept everything roll related on the bottom, but I'm just doing it this way. Now it says how much, so that means that we're after the price. We're after the price of something. So where my $sign is, I'm putting X on the bottom. How much would it cost to purchase 40 rolls? So I highlighted the 42, so I'm going to leave it like this. Now, as it's the same rate, we know that these two are proportional, so we let it equal. And so to solve a proportion, there's a few ways to do it. One is to cross multiply. Now before I cross multiply here, to make things a little easier for us, I see that 16 over 10 can be simplified. I can divide by 2 to the top and the bottom. So dividing by 2 for the top gives me 8. Dividing by 2 on the bottom gives me 5. So now when it comes to cross multiplying these, it's a little easier when I take my 5 and I multiply it by the 40. That's when I get my 200. And when I take the 8 and I multiply it by the x, that's when I get 8x. So now this is just a one-step equation. So in order to get the x on its own, which is the how much from our question, we just do the inverse operation. So as it's 8 times x, we need to divide by 8. And that will cancel them out and leave me with the x. But if I divide by 8 on one side, I must do the same on the other. And so 200 divided by 8, that gives us an answer of 25. But we're not done yet. If we just leave it like this, we're basically not going to get paid. And we want to get paid. If we're doing all this hard work, we want to make sure we get paid. So in this case, x does equal 25, but when we check our question, how much would it cost to purchase 40 rolls at the same rate? If we just said 25, it's not really answering how much. We don't know if we're paying $25 or 25 cents or 25 anythings, 25 peanuts. We don't really know. So we've got to write our answer, which is, and really if you write it as a sentence, it's actually seeming a little more coherent as well. So it will cost $25 to purchase, and using the same verbs like purchase is in the question, purchase is in our answer, it helps us check that we're doing the right thing. So it will cost $25 to purchase 40 rolls. And this is a great answer. So that was number 2. Okay, so for number 3, we're told that triangle ABC is a similar triangle to triangle XYZ. And then we're given some dimensions as well. So we're told that AB, which is one of the sides, is 10 centimeters. We're told that BC, which is another side, is 12 centimeters. And we are told that AC is 8 centimeters. And finally we're told that XY, which is of the other triangle, is 22 centimeters. So for question 1, we're actually asked to basically give a definition of what it means when a pair of triangles are similar, when they are similar. So we've got to ask ourselves, have we heard this word before, similar? Similar triangles, similar figures, and so hopefully we have remembered that similar triangles are, so let's write it, similar triangles are proportional. That's what it comes down to. Proportional. Which means that all sides are in the same ratio. Which basically means that if you double the sides of AB to get to XY, you would also double BC to get to YZ. And so that's what it means when all sides are in the same ratio. And so similar triangles are proportional. That's the key thing here. So as we move on to B, we're basically going to have to do some labeling right now. We're told that AB is 10 centimeters. So I'm going to not write my units here, but we do need to remember this is centimeters. We're told that BC is 12 centimeters. We're told that AC is 8 centimeters, and we're told that XY is 22. So XY is 22. Now we're trying to find out what xz is, so that's right here, xz, and we're also trying to find out yz, which is right here, yz. And so in order to do that, we need to firstly come up with our first ratio. So as we look at this, in this shape here, let's call it B for big, and let's call this one S for small. In the big shape, the only side that we know is 22. And so what we can do is we can first pick that 22, which is from the big, and we can compare it to its corresponding side in the small. So the corresponding side when we compare 22 is going to be the 10. Those are the corresponding sides. So I'm going to put that over 10. And in order to create a proportion to try and solve this thing and find the missing sides, we need to pick another ratio. So let's pick xz, which is right here. Now as xz is from the big, that must also stay on the top because B is there, 22 is from the big, so xz must also be from the big, so it must go on top. Now xz corresponds with 8, so we're going to put the 8 there, and as it's a proportion we're going to let it equal. And again, I'm seeing that we could just cross multiply here, but because 22 and 10, they're both divisible by 2, I'm going to cross this out. 22 divided by 2 gives us 11. 10 divided by 2 gives us 5. So now when I start to cross multiply, I'm going to do my 5 times xz, which is going to be 5xz, and I'm going to let this equal 8 times 11, which is going to equal 88. And so now in order to find xz, I'm going to divide by 5, and then I'm going to have to do the same to the bottom. So divide the bottom by 5 as well. And so my 5's cancel out, and I'm left with 88 divided by 5, which gives us an answer of 17.6. So xz equals 17.6 centimeters. So remember, if we want to get paid, we've got to, after we do all this work, we need to write the units, and we need to write our answer very, very clearly. So sometimes it's well, actually almost always, it's a good idea to put your answer in a billboard. I want to make it nice and clear so we box it up. So that was our xz. But if we just moved on now because we felt we did a lot of work, then we'd be only getting half of these points. We'd only get 2 out of the 4 points because we didn't yet find yz. So let's try and do the same again. We're going to create a proportion where we do the big compared to the small. So we can stick with our original, which is 22 over 10. Remember, this same ratio must work for all the sides. And so this should equal, now what are we looking for? We're looking for yz, so I'm going to, let me put an orange circle around this. yz corresponds with this 12. So therefore, what I'm going to do is put my yz on top because that is part of the big shape. And I'm going to compare this to the corresponding side on the small shape, which is 12. And again, I can simplify this first ratio, which becomes 11 over 5 when I divide by 2. Now when I cross multiply, remember up here I did 5 times xz, and then I did 8 times 11. That's how I got the 88. So here I'm going to do, again, 5 times yz. So it's going to be 5yz. And this is going to equal 11 times 12, which is 132. So the step is inverse operation. If it's being multiplied by 5, you need to divide by 5. That gets rid of it. We've got to do the same to the other side. We divide by 5. And so we are left with 132 divided by 5, which gives us an answer of 26.4. So yz is going to equal 26.4 centimeters. And as we've been pretty neat so far, let's box this one up as well, and then it will be very clear where our answer is. So just check around. We answered this question, we got our 2 points, we got our 4 points here, we've shown all of our work. This is a good job. Okay, so let's move on to question number 4. Okay, so in this case we've got to highlight some stuff. There's so much going on here and we don't want to miss it. So Matt lives in Great Britain and wants to buy a laptop. The best deal he has seen is for £400. So we've got to be careful. That's not dollars, that's pounds. Next month, he's planned a trip to the United States and has seen the exact same laptop there for $590. So I'm already seeing we've got different units here. So we don't know if 590 is necessarily more than 400 because they're different units. After checking the exchange rate at xe.com/UCC, which is just a website that shows currency exchange rates, he sees that the current exchange rate is 1 GBP equals 1.52 USD. So GBP is Great British Pounds, so that's just our pound sign, and USD is United States dollars. So the real question is, if the exchange rate stays the same, will Matt, so this is what we need to answer when we finally get our answer. Will Matt save money by waiting and then purchasing the laptop in the United States? Or should he buy it in Great Britain? Show all calculations and explain below. So I see up here this exchange rate 1 GBP to 152 USD. That's our first ratio. So if we're going to do pounds compared to dollars, we can say that £1 is the same as $1.52. So we're going to leave it like this. Now, the issue was which one's cheaper. Is the £400 the better deal, or is the $590 the better deal? The $590. So what we need to do really is, if we focus on this £400 and convert this to dollars, then the dollar price here we would be able to compare with $590. So we're going to set this up as a proportion. We've got £1 is compared to $152, and we've got £400, so that's going to go on top because that's where our pounds live, and that's going to be compared to the dollar equivalent. So this is our proportion, and really that's really what a lot of these 5 points are for. So in this case we're going to cross multiply. So we're going to take our x and times it by the 1, so that gives us 1x, which can just be written as x, and that's going to equal 152 times 400. So 1.52 times by 400 is going to give us 608. 608. So if we clean this up a little, we don't need this 1 there, so we could just write this as x equals and then $608. So we just worked out that £400 is the same as $608. So now we can compare 608 to 590, and so if he buys, we can even write this as our answer. So we're told to show all calculations, which we did, and explain below. So if he buys the laptop in Great Britain, it's £400, which we were told, which is the same as $608, as $608 is more than the $590. Matt's better off if he buys it in the States. The United States. So, you know, obviously he wouldn't take a flight to go buy it, but if he was making a trip anyway, and if it wasn't urgent for him to have a laptop immediately, then maybe it's a good deal for him to buy it in the States. But, you know, you could go on to explain a little more and think that really this is only $18 cheaper. And so that $18, if he buys a laptop and then, you know, something goes wrong when he takes it back to his country and he can't return it to the store, then that could be a big problem as well. But this is good enough to get our 5 points, and it's always good to keep thinking beyond the problem as well. Okay, so that's a good job with this question. Okay, so this is question number 5, and this is also another wordy problem, real world problem, and so it's probably best that we highlight what's important. So Martha's family bought her an electric scooter for her 80th birthday. She couldn't wait to try it and hopped on straight away. She found that she could travel 1/4 of a mile in 1/3 of an hour. So this seems like it's pretty important. Some math stuff. The next day she planned to ride it to the grocery store that was 2 miles away. So I think 2 miles is probably important. And then we're asked, how long will it take Martha to travel to the grocery store? So things like grocery store aren't important in this question. It could have been travel to the museum, travel to school, travel to work, wherever it was. But how long will it take is important to get to the 2 miles, the thing that's 2 miles away. So let's see, there's a couple of ways to actually get started with this one. So the first way, because I see 1/4 of a mile in 1/3 of an hour up there, that's a ratio. So miles are a measure of distance, and hours are a measure of time. So I'm going to put d over t now. This is just kind of my key to remind me that I'm going to keep distance on top. So I've got 1/4 of a mile, and that takes 1/3 of an hour. So this kind of looks weird, fraction on top of fraction, but this is okay as long as we fix it at the end and we don't get too mixed up. 1/4 over 1/3, 1/4 of a mile in 1/3 of an hour. And so that's our first ratio, and we're asked for how long will it take. So that's our time. We're trying to figure out the time, so I'm going to put an X there, to go somewhere that's 2 miles away, so my 2 can go on the top. So if it takes 1/4, if it takes 1/3 of an hour to go 1/4 of a mile, we are looking for X, the time it takes to go 2 miles. So we're going to let this equal. This is a proportion, 2 equal ratios. So now I'm going to do my 1/3 times 2, and so 1/3 times 2. And if you need to, you could think of this as 2 over invisible 1, but really we need to start thinking that when we have a fraction times by a whole number, the whole number is only going to affect the numerator. So 1/3 times 2 is the same as 2/3. And then we are doing the other cross multiplication from x times 1/4. So 1/4 times x, and you could think of this again as x over an invisible 1. And so the x really is only timesing by the 1, which equals x over 4. So let me write the results of this underneath, which is when we did the 1/3 times 2, we got 2/3. So 2/3 equals x over 4. Now, in order to get x on its own, when it says x divided by 4, we need to multiply by 4. So that's our inverse operation. We're multiplying by 4 to get rid of this divide by 4. But whatever we do to one side, we must do to the other. So the work for this 2/3 times by 4 right now, so let's write it 2/3 times by 4. So we could put the invisible 1 under, but this time I'm not going to. let's try and do it without seeing this invisible one. We just multiply across the top. The whole number only affects the numerator. So that gives you 8 over 3. So carrying down with our equation here, we've got 8 over 3 equals x. So x really was how long does it take, and our units up here for a third of an hour were hours. So you could argue that x equals 8 over 3 hours, and you would be correct. But we don't like, and we don't really need to leave this as 8 over 3. It's an improper fraction, so we could simplify it. 3 into 8 goes 2. Our remainder is 2, and our original denominator was 3, so this is also the answer. 2 2/3 hours. But even going a little further, we could try and understand what 2/3 of an hour means a little more. As each hour has 60 minutes in it, each hour, full hour, is 60 minutes. If we were to break this into 2/3, actually, if we were to break it into thirds, we would see 1/3 is 20 minutes around, 2/3 is 40 minutes, and then 3/3 would be back up to 60 minutes, although it starts at 0, goes to 20, 20 to 40, 40 to 60. So the 2 hours and 2/3 would mean that we get around this much for 1/3, and then we get around another 2/3. So from this little picture, maybe we can see that 2 2/3 hours equals 2 hours and 40 minutes. 2 hours and 40 minutes. And really, you know, if we've got time in the test, why not wrap this up really nicely and say a sentence, which is, it will take Martha 2 hours and 40 minutes to travel. Notice again, we're using the verbs that are in the question. This is going to help us not make a mistake. It will take Martha 2 hours and 40 minutes to travel to the grocery store. And that's it. And we've shown our work, and we've shown everything, and it is great. Okay, so I just wanted to show one other method of solving this problem that is more to do with logic and scaling. Logic and scaling. And so these are two very important tools to have in your tool belt to be able to solve problems like this. And although they're connected with ratios, it almost seems as though you're not using ratios when you solve this. So let's take a look. We know that Martha traveled 1/4 of a mile in 1/3 of an hour. So one way to do this is to get rid of one of these fractions by, here in this case we're going to times by 4, and that turns it nicely into 1 mile. But then we've got to do the same to the other side, times by 4. So therefore it took 4/3 of an hour to travel that far. So the next thing to do, because we're trying to find how long it takes to go 2 miles, we've then got to times by 2. Same over here, times by 2, so we end up with 2 miles takes 8 over 3 hours. And this equals 2 2/3 hours, which itself equals 2 hours and 40 minutes. And so we could leave our answer like this. Now, that's it. That's the answer. We did that by scaling, by seeing if we had 1/4 of a mile in 1/3 of an hour, we need to times by 4 to get 1 mile, and then times by 2 to get 2 miles. If we'd have seen that we could go directly from 1/4 of a mile to 2 miles by times by 8, we could also have done the same over here. 1/3 times by 8 gives you 8/3, and then we could simplify and get our final answer as well. So this just shows you more than one way to solve these types of problems, and this is perfectly acceptable, and it shows all of your work too. Okay, so for number 6, we have a long word problem here. So let's see what's going on. Let's get our highlighter ready. So we're told that the Statue of Liberty's face is 8 feet high. So face 8 feet high. We're told her feet are 25 feet long and her waist is 35 feet wide. So see picture below where these dimensions are labeled. So I see two pictures. I see a photo and I see Peter's poster. So the labels here, 8 feet, 35 feet, and 25 feet, they just match up with those numbers that we've already been given. It says Peter created the poster below on the right, but he feels that his painting isn't truly to scale. So maybe this is important, but I'm going to highlight isn't truly to scale. We're not sure if that's true, so I'm even going to go back on that and put a question mark because he's not sure. Okay, if we keep looking around, he painted the statue. With a face height of 28 inches, which is over there. 28 inches. A waist of 122.5 inches, and a foot length of 75 inches. Peter has labeled the measurements for the dimensions of the statue in his poster. Use this information to show if the poster is or isn't a scale version of the real statue. Alright, so if this is a scale drawing, just like the similar triangles example, all dimensions, all sides, all heights, all widths would be in the same ratio. So as we look across here, we've got, we've got something that's labeled on both sides. We've got all of them labeled on both sides. So let's compare our 28 inches to 8 feet. So let's do, let's go big picture to small again. So this is big and this is small. This is going to help me not make a mistake. So going from big to small for the face, we've got 8 compared to 28. And if it's proportional, this should equal, so I'm going to put question mark, this should equal 35, which is on the big, compared to 122.5. So let's see if these two are in proportion. So if I cross multiply them, and first let's simplify them a little. So let's see, 4 goes into both of these. If I divide 8 by 4, I get 2. If I divide 28 by 4, I get 7. So this is the same as 2 over 7. So now, if I use my 2 over 7 in the cross multiplication, I got 7 times 35. So 7 times 35 is going to give us 245. 245. And we're seeing if that equals the other ratio after we cross multiplied, which is 2 times by 122.5, and that also gives us 245. So because 245 equals 245, these two ratios, which involve the head and the waist, are proportional. So far it's looking excuse me. So far it's looking like this is a proportional relationship. So it's looking like it is to scale. But we need to check the feet. So let's go back again, and we're going to do big to small, but this time we're comparing the feet. So we're going to start off with our 8 over 28, which was the faces. That's one ratio. And we're checking question mark if it equals the same as the feet. So 25 feet for her feet compared with 75 inches. So notice big to small, always the big numbers. Well, the big statue, the big photos numbers go on top, and then the small, the posters numbers go on the bottom. So again, I can simplify this first fraction, makes it a little easier. 8 divided by 4 gives 2. 28 divided by 4 gives 7. So this time we're going to cross multiply, and we have 2 times by 75. That gives us 2 times 75 gives us 150. And although I didn't draw it up here, we multiplied both ways. And so now I'm going to do 7 times by 25, which that gives us 175. Question mark. Now 150 does not equal 175. So in this case, what we should do is just firstly check that we did the math correctly. So 2 times 75, that does give us 150. Now I know 7 times 25, well, 4 25s are 100. Then I've got 3 more 25s, which gives us a 75. So this math is correct. And so this tells us that the feet are actually not the same ratio as the heads together and the waist. So because the feet are not the feet at the bottom here and the feet at the bottom here, because they are not proportional, this isn't to scale. So it says use this information to show if the poster is or isn't a scale version. So we're trying to show if it is or isn't a scale version. So after we do this, we can say the poster is not a scale. So again, using the question, we're making sure that we're on track. The poster is not a scale version of the real statue. And we could go on to say because of the feet, because the feet are not in the same ratio. And our math has shown that as well. So that was question number 6. Okay, here is number 7, A and B. And this is an interesting question. And it involves a hot dog eating competition. So let's take a look. So we're told that Kevin can eat 19.5 hot dogs in 2 minutes and 30 seconds. So we're asked for his unit rate. So let's take a look. The first thing that we need to remember is what is unit rate in this question. So unit rate is always something, is a comparison of two amounts, but the second amount is per 1. So it could be the number of miles per 1 hour, per hour. It could be the number of hot dogs per minute, in this case. Or it could be the number of hot dogs per second. Or it could be how fast a tree grows per year, per 1 year. Those are all examples of unit rate. So this is really how we address this question. We know that he eats, so I'm going to put an E, and I'm going to put T for time. So he eats 19.5 hot dogs in 2 minutes and a half. So I'm going to put 2.5 minutes. So this is the ratio. Now to get the unit rate, we want this to be per 1 minute. And at the moment, we only know how many he eats per 2.5 minutes. And so in order to find the unit rate, what we must do is just divide. So we are going to take 19.5, which is 19.5, and we're going to divide this by 2.5. And that's going to give us our unit rate. And so 19.5 divided by 2.5 is going to give us an answer of 7.8. So 7.8 is our solution, but really our answer needs units. We were asked for his unit rate, so it's 7.8 hot dogs eaten per minute. So we can write per minute just as this. And if we want to make it super clear, we could box up our answer. And so there we have it. 7.8 hot dogs eaten per minute. That was his unit rate. Okay. So B is asking us if Kevin maintained this hot dog eating rate, how many hot dogs would he eat in an hour, in 1 hour? So if he does 7.8 hot dogs per minute, then in 1 hour, which is obviously 60 minutes, he's going to do 7.8 hot dogs times by 60. So this is one way to think of this unit rate, 7 as the number of hot dogs per minute. So in 60 minutes, he's going to do 7.8 times 60, because he's doing 7.8 hot dogs every minute, and we have 60 minutes. So this is one way to do it. So we can take our 7.8 and we can multiply by 60, and we're going to get a huge number. In fact, this is probably an impossible number in real life for him to eat 468 hot dogs. Okay, but we're just going to pretend it's believable given this question. Now, the other method to do this, let me do this in different color, is if he eats 7.8 hot dogs, so I'm going to put my H over there, and the time is on the bottom, so per minute, per 1 minute, that's our first ratio, 7.8 over 1. And we're going to let this equal some number of hot dogs in 60 minutes. So this is how we can do it, using a proportion. And so we would then cross multiply, so we do 1 times x, which would be x, equals 60 times 7.8. And so in effect we're doing the same thing. Up here we did 7.8 times 60. Here we're doing 60 times 7.8, and we get the same answer, 468 hot dogs. Okay, but notice here we set up a proportion, there we just use the unit rate. Okay, good job, that's number 7. Okay, question number 8. This is also a very interesting question, and something that could save you a lot of time and money in future as well. Okay, so let's see what we've got. Let's highlight the important bits of information here. If half a gallon of paint covers 2/7 of the wall, if half a gallon of paint covers 2/7 of the wall, how much paint is needed to paint the entire wall? Okay, so here we've got a comparison of two amounts. So we've got a ratio from the start of this question. We're told that the number of gallons to the amount of wall, G compared with W. So the number of gallons is half a gallon, gives you 2/7 of a wall. Half a gallon gives you 2/7. And what we're looking for is how much paint. So really, I should have highlighted that, because that's a crucial thing that we're looking for. How much paint is needed to paint the entire wall? So the number of gallons of paint is needed, X, to paint the entire wall. So the entire wall is going to be 1, because that's one full wall. So in this case we can cross multiply, which is to do the 1 times a half, which gives you 1/2, and then we're going to do 2/7 times x. So when we do this, 2/7 times x, again we could think of this as x over 1 over an invisible 1, and that would give you 2x over 7. And keep in mind that this is exactly the same as saying 2/7 x. Now the x could live higher up with the numerator, as you see over here, but the x cannot live on the bottom with the 7. That would be a completely different answer. So what I'm going to do is, we already did the 1 times a half to give us 1/2. We're going to let that equal 2/7x. Okay, now we still got some work to do, because we're almost at x, but we have this coefficient of x, which is a fraction. Now we could do 2 steps. We could times by 7 and then divide by 2, but there's one move that we can do here that will get our x on its own. So we need to try and tackle this 2/7, and if we want to turn 2/7 into 1, we need to multiply by its reciprocal. So we flip it upside down and we're going to multiply by 7 over 2. And what this does, it turns it into 1, because let's do it over here. 2 over 7 times by 7 over 2. These itself are going to give you 14 over 14, which equals 1. And 1x equals x. So this got us our x on its own. When we multiplied by the reciprocal, they cancelled out. And remember, the reciprocal is also called the multiplicative inverse. Now, if we multiply the right-hand side of this equation by 7 over 2, we must do the same to the other side. So times by 7 over 2. So in this case, we've got 1/2 times by 7 over 2. So we're just going to multiply across. That's 7 over 4. So in this case, x equals 7 over 4. And we could get our answer at the end, put the x first, and then simplify this a little. It's an improper fraction. So x equals 4 into 7 goes 1 whole time. The remainder is 3, so it's 1 3/4. Check our question again. How much paint? Now, we were told 1/2 gallon before covers 2/7 of the wall, so we're dealing with gallons. So x equals 1 3/4 gallons. And if you converted this to a decimal and said 1.75 gallons, that's also correct. So that was the answer to question number 8. Okay, let's take a look at number 9. Okay, for number 9, we are asked if this is a proportional relationship. So let's go through the question and do our highlights. So consider the prices in the table below for different numbers of books. So the question is, do the numbers in the table represent a proportional relationship? Show any work and explain. So as I look on this table, I see a few things. I see the number of books and the prices. So when we compare 1 to 4, when I think about proportional relationships, I think about multiply. So sometimes you can see it easily. So in this case, 1 turns into 4 by timesing by 4. 3 to 12, well, that's times 4 again as well. So it's starting to look proportional. 5 times 4 also works out. We get 20. And 8 to 36, well, 8 times 4 would give us 32. So this isn't times 4. This last one is actually times something else. It's not times 4. And whether we see it or not, it's not the biggest deal, but we know it's not times 4. And because this times 4 does not give you this, the proportional relationship breaks down here. So the question is, do the numbers in the table represent a proportional relationship? So your answer would be no. The numbers do not represent a proportional relationship. Now, there's going to be a few ways that we could use to explain this. So we could use the idea that we scaled the numbers by times 4, or we could, really show how smart we are, and we could start using this proportionality equation, which proportionality equation works for these 3, which is y equals times 4, so that was our constant of proportionality, x. And that's where the number of books was our x, was our input, and the price which came out was our y. So we could label it here as well. So if books were 3, the price came out as 4 times 3 came out as 12. But this only worked for the first 3. So we could go on to say, no, the numbers do not represent a proportional relationship. The first 3 numbers add, or in fact I would say fit the equation y equals 4x, but I actually cancel that. I would say but $8 did not. And you know, there's more that we could write, but I think we did enough here showing the work on the table. We've discussed the proportionality equation here as well, and we've clearly shown that 8 to 36 is not times by 4. So I think this is good enough to get the 4 points for this particular question. Okay, number 10. So let's take a look what's happening with number 10. So Mary works at Super Duper Supermarket and she earns $15 per hour. So that's going to be important. We're asked to write an expression. Let's highlight that. We need to write an expression to represent the amount of money she earns. So the amount of money she earns. And don't forget to define variables first. So let's see, we need to define some variables and write an expression. So I know an expression doesn't have an equal sign. So I don't need it to be an equation. So what we could do is say, I know it's 15 is important up here. So she earns $15 per hour. So 15 times H would be the amount of money she earns, where H is the amount of hours that she works. So defining a variable means that we have to say let, and then I'm using H equal the number of hours Mary works. Okay, so 15H is the actual expression to represent this relationship between amount of money she earns and the amount of time that she works. So as this is a proportional relationship, what is the constant of proportionality in your equation? Well, really this should say expression here because it asked us to write an expression. But in this case, if E is the amount of money she earned, E equals 15H. So this looks very, very similar to the proportionality equation, which is Y equals KX. So in this case, the K matches with 15. So we could now go on to say that the constant of proportionality is, so we could say the constant of proportionality is 15. There we go. Constant of proportionality is 15. Now, what are the other names for the constant of proportionality and what does it mean? Well, the other names, so this is just really remembering work, but the other names are slope, rate of change, now constant of proportionality was already given to us, but that is also one of the things to remember that K is. So we've got slope, rate of change, we've got K, maybe they would want to know that. K is in the equation Y equals KX. And then also finally we've got unit rate. Now what does it mean, we're asked? Well, the constant of proportionality, with aka the unit rate, or the constant of proportionality gives the amount of change in one variable as the other increases by 1. So let me explain what this means. For the hot dog eating guy, he ate 7.8 hot dogs per minute. That was his unit rate. So if his time increased from 1 minute to 2 minutes, he would eat another 7.8 hot dogs. So every minute he was doing 7.8. So the constant of proportionality helped us understand unit rate in that case, and it tells us the amount of change in that one extra incremental time period. But it could be the amount that a tree grows in 1 year. It could be the increase in the cost of books after you purchase one extra book. So unit rate is always per 1, and unit rate is the same as the slope of a graph, if you were to graph the relationship, and it's the same as the rate of change. It's called K, and it's the constant of proportionality. So I think that we did enough there to get the 3 points. Okay, now question number 11 is actually similar to the example I just gave with the tree. So let's do a little highlighting, a little bit of a question survey. We're told that an elm tree grows 5 inches each year. And we're told to graph this proportional relationship, and don't forget to add a title, label axes, and choose an appropriate scale. So we're told a few things here. So let's get started with choosing what's going to go where. So we know that this is our x-axis and this is our y. So the x-axis, we've got 5 inches per year. So we've got growth in the height, which is in inches, and we've got time, which is years. Now I've put time and years on the bottom because it's the independent variable. The time in a line graph is most often on the bottom because it does not depend on the height in this case. Time goes on its own and very little can change time. But time, however, the more time that happens, the taller that this tree will get. So height is dependent on the time, and so the dependent variable goes on the y-axis. Now, I'm going to choose a scale. Now, we know 5 inches per year, so I'm going to choose 0 years, 1 year, 2 years, 3 years, 4 years, 5, 6, 7. So those are my years. Now, I'm going to put 0 on the bottom for height, because when the tree comes from a seed and it first starts to grow, it's after 0 years is no time, it's not grown at all. But then as I go up, because it's growing 5 inches every year, I'm actually going to jump in 5s. I think this will be a nice scale. 0, 5, 10, 15, 20, 25, and so on. So now let's think about this. After 0 years, the tree didn't grow. After 1 year, it grew 5. After 2 years, it grew 10 inches, 3, 15. So this is the pattern that we get based on this up at the top, 5 inches per year. And so what we should be able to do here is actually grab a line, and we should be able to make a line that's perfectly straight through them all. So there we go. We've got a line that cuts straight through all of these points. And so that shows our proportional relationship. It's a straight line through the origin, so it's proportional. Okay, so let's take a look at the next. Okay, so it says write an equation to represent the relationship above. So above is meaning back in our table we need to write an equation for this. So we could make a table and start thinking about the relationship. So x compared with y. So when x is 0, y is 0. When x is 1, y is 5. When x is 2, y is 10. When x is 3, y is 15. And so on. So here I see that my y, my output, equals whatever goes in. So in this case it's 1 goes in and it turns into 5. So that looks like a times 5 relationship. Does it work for everything? Times 5. It does times 5, and it even works for 0 to 0. Times 5. So in this case, the relationship can be represented by y equals 5 times whatever x is. And this equation is our proportionality equation, and 5 is that slope. It's the rate of change, and it's the constant of proportionality as well. So y equals 5x. So I'm going to go back to the other question, write that in. So y equals 5x. Question 2, the point 315 should be on your line above. How can we interpret this point 315? So let's go back and take a look. 315 should be on here. Well, it is. 3 and 15 is here. And this shows us from 3 years, the tree's height is 15 inches. So let's go back. 3 years, the height is 15 inches. So the 0.35, well, 3 is our years, and 15 is our inches. So how can we interpret this? We can interpret it as, so let's use the verbs that are in the question. We can interpret this as the tree grows 15 inches in 3 years. So I think that we got those 3 points there just from that. Okay, next let's take a look. The point, so I'm going to highlight some stuff here. So the point 1, r is very important with proportional relationships. So it wants to know why is it important and what does it represent. So it's asking us a few things. Then it says make sure you use appropriate explanations with mathematical vocabulary. Okay, so we've got to make sure we do these things now. So 1, r. So let's go back briefly to the question. 1, r. So on our graph here, we know that 1, r is going to be where x, let's just put it over here, 1, r. We know that this is in the format of x, y. So 1, r is always where x is 1. So as we go up and go across, that must mean that in this case r equals 5. So why is this important, r equals 5? Looks to me like 1, r gives us the unit rate. So it gives the unit rate. It's no coincidence that up here we have 5x, because 5 is our slope, it's our unit rate, it's a constant of proportionality, it's a rate of change, and so r is revealed. The unit rate is revealed at r, at the point 1, r. So if I go back, we could even just write that in directly. We could say that 1, r is important because r is the unit rate and that's also the constant. So we're using our math vocabulary right now. Constant of proportionality. And so I think that's pretty much it. Let's just check. The point 1r is very important with proportional relationships. Why is it important? Well, we've said it's important because r is the unit rate and the constant of proportionality. 1, r is important because... Alright, and so I must go on to say a little more. this point, so we're talking 1 comma r, can show us the unit rate quickly and easily by reading the graph. Okay, make sure you use, I think we did pretty well. What does it represent? We said it's a unit rate. We could go on to use some of the other definitions. We could say it's the rate of change or the slope. So maybe I would actually add that as well. I'd say R is also known as the slope of the line. I think we did a pretty good job with this question. Okay, let's move on. Let's take a look at number 12. Okay, so what's going on with 12? Alright, so Aaron has made a scale drawing of his garden, which includes a rectangular swimming pool, so we know it's a rectangle. His drawing is to scale, so it is to scale, and it's 1 inch is 12 feet. So before I do anything else, I'm going to write that down, just so I don't forget it. We know that the drawing is from inches. You know, actually, I wouldn't even put inches there. I would just put, alright, let me get rid of that. I would put 1 to 12 is, you could put them here, I guess. 1 inch to 12 feet is the ratio of the scale drawing to the actual. And you can use any letters over here. I'm just putting the drawing to the actual. If the dimensions of the pool in his drawing are 3.5 inches by 9 inches, so let's plot this out. So let's draw this out. So his rectangular pool is here. We know 3.5 inches by 9 inches. So if the dimensions of the pool in his drawing are 3.5 inches by 9 inches, what is the actual area that the pool will take up? So, right, so I see. So that's his drawing. It's a little rectangle, but the real rectangle is obviously going to be much bigger even than this. But it wants to know the area of it. And over here, when I started writing this, this is just our scale. This is the almost like the blueprint. This right here is our actual. And what we are looking for, if I go back up to the question, is what is the actual area of the garden? So it means that we need to find out what's the area of inside of this larger rectangle here. So in order to do that, I need to find the length and the width. So I'm trying to figure out what 9 turns into to get over there. And then that's going to tell us our length, and then try and figure out what 3.5 turns into for this dimension. And then we just multiply the two of them together to get our area. So let's see. 1 inch is to 12 feet. So therefore, if we've got 9 inches and 1 inch is 12 feet, we really need to times this by 12. And we can put feet over here, because it's going to be feet. And again, we've got to times by 12. And that will give us our feet. So that's one method of doing this. And remember, whatever we get for the area, which is 1 times the other, the units of feet squared. So it doesn't hurt to fill that in right from the start. Now the other way to have done this is to think, what, 9 is to 3. So in fact, I think that this is the best way right now. It's just to do this. We could have called one x, but I actually think that this is the best way. So if we do 9 times 12, 9 times 12, we get 90, we get 108. So this one is going to be 108. And if we do 3.5 times by 12, what we're going to get is 42. Let's just set this up. So we're going to do 3.5 times by 12. And in this case, we almost want to forget about this decimal point and just think of it as 35 times by 12. So in this case, 2 times 5 gives me the 10. So I would just put my 0 and carry the 1. 2 times 3 is 6, plus the 1 is 7. Then I would do 1 times 5, but because I'm 1 over, I'm going to put the x. 1 times 5 is 5. Then 1 times 3 is 3, so I put that there. Then add them up, and I get 420. Now the trick, because there was that decimal that was in there, is that we need to go back to our original number and count how many places over the decimal is. In the first number, it's 1 space over. In the second one, the decimal is right at the end, so it's 0 spaces over. And then I would add these two. So the total number of jumps is 1 plus 0 is just 1. So then we've got to put the decimal point back in 1 space over. So that's the sum of the two others. So our final answer here would be 42.0, which we don't need. So let's go back up and put in our 42 here. So now the area of this thing is going to be 108 times by 42. So let's do that. 108 times by 42, which is going to equal 4536. 4536. And so that's our answer to number 12. Okay, so number 13. Let's take a look at 13. So we're told last weekend Mike took a trip to visit his grandmother 210 miles away, so maybe that's important. The graph below shows the distance, which is right here, the distance in miles of Mike's journey at different stages of the trip. So the times on the bottom, I see that. So the first stage is between 0 and 1. The second stage is between 1 and 3. I'm coloring these different because I see that this isn't a proportional relationship. This isn't a single straight line. This line changes the angle, it changes the slope. And then from 3 to 5, something interesting looks like it happens from 3 to 5 is that the distance stays at 100. So it looks like he took 2 hours off and just didn't even move anywhere here because the line stays flat. And then between 5 and 7, the line starts picking up again and it goes all the way up. Now, the question is, what was Mike's average speed from 5 to 7 hours? So we really are focusing on this piece right here, 5 to 7 miles. And we want to know his average speed. So when we think of speeds, we think of a speed as something like 50 miles per hour. That's the speed. So it's miles per hour, or we think of 120 miles per hour, or whatever the number is, but it's something miles per hour. And you could write it like this, or you could write something mph. And I write this because if we think of it as miles per hour, we're thinking of miles, so many miles over so many hours. That's why our units are miles per hour. So between 5 and 7, we've got to think how much time passed. Well, we can do 7 minus 5. That gives us 2 hours. Now in 2 hours, we need to find how many miles he drove. So he drove from 100 miles away all the way. Actually, it looks like it's well, actually, we're told right in the question up here, we're told that he took a trip. we took a trip that was 210, and if this is roughly 1/5 of the way between 200 and 250, then this should work out over here, which makes sense with our question, as 210. So he went from 100 all the way up to 210. So therefore the difference is 210 subtract 100, which means that he traveled 110 miles. Now, we were after what's Mike's average speed, and that should really be a capital M as well. So what was Mike's average speed from 5 to 7 hours? So we've got a rate here, which is 110 miles every 2 hours, but for it to be an average speed, we need the unit rate. So we've got to divide this by 2, the 110 divided by 2. So 110 over 2 equals 55. And so his average speed, so we can say Mike's average speed was 55 miles per hour. And you could write this as 55 miles per hour like this as well. Okay, so that's the end of this Unit 5. And so if you were stuck on anything, please go back, maybe give it a break for a little while, then return later. You know, if you wanted to review some of it now, that's great, but it's always worthwhile doing this after some time has passed to see what we really know for sure, and also sometimes things take a little while to sink in before we learn it. But this is one of the most important units, and so it's very, very important that you understand everything that's in this video and that's on your unit test sheet. Okay, and just one last thing to remember, and that's accountability checklist. It's great that you're reviewing this video, that you're following along and making corrections and checking all your work that you've got right. But it's also equally as important to make sure that you're paying attention in class, also to keep up with the class notes, and to make sure that everything's written neatly so that you can read it, so that it's well organized. Math is complicated enough without your work being messy and difficult to read. Also to make sure that you complete all the homework and that you ask questions when you need help. So please do make sure that you're doing all of these things in class